All right, so let's review very briefly Newton's laws, Newton's first, second, and third law of motion that are, and then we'll see how does everything apply to the uniform circular motion, an extension pretty much of these laws. So the first law is known as the law of inertia. Pretty much it answers the questions why do objects have an acceleration zero, why they don't accelerate, or why do objects stay at rest, which means why is velocity zero, or why do objects have constant velocity, right? Or uniform motion. By the way, all these three states are the same thing. We cannot distinguish from one to another. Constant velocity, so which means uniform motion. Okay, and pretty much the answer is why don't they have an acceleration? Because the all the forces acting on that particular object are balanced. All right, or the net force is zero. Okay, very important to know that to use Newton's laws in a valid way, we need to measure everything from an inertial frame of reference. Okay, so inertial frame of reference is are frames where Newton's first law is valid, which means the things are measured from an object that is has zero acceleration. All right, which means they're not rotating, they're not accelerating. Non-inertial frame of reference are the opposite of this one. Let's write very quickly Newton's first law. And mathematically, Newton's first law, I use this NIL just as an acronym. So F net is actually equal to zero. And this is an acronym, sorry, it's a synonym to the fact that the acceleration is zero or velocity is constant. They all mean the same thing, or we're dealing with uniform motion, right? We're gonna write it in always. And whenever we need it, we're gonna write it in component form, especially if forces are in two dimensions, right? So we usually choose a frame of reference, and then with respect to that frame of reference, we say that F net x and F net y are both zero. All right. So this is Newton's first law in a component form. That's Newton's first law in a vector form. All right. So that's how we're going to use Newton's first law in either form. Then we have Newton's second law. So the Newton's second law will tell us why do objects have an acceleration, right? Pretty much anytime the forces acting on an object are unbalanced, which means there is a net force that is not zero, there is an acceleration. That's pretty much a given. But not only that, Newton figured out that this acceleration is proportional to the net force and however is inverse proportional to the mass of an object, which means that remember what we said about the mass is the ability to resist changes in motion, right? An acceleration is a change in motion, if you recall. Okay, so anytime there's a change in motion, either direction, magnitude of velocity, there is an acceleration. So the relationship, the proper one is acceleration equal to, so proportional to F net, we write it like this, right? This F net over mass. Or on the most standard universal form that we've seen it everywhere is F net equal to mass times acceleration. All right. Please remember that it's F net, that not just F equal to ma. All right. The same idea, since it's a vector, we have to write it in a vector form, and sorry, in a component form. And in a component form in general, remember we're free to choose our frame of reference, our coordinate axis. Since F net is a vector, we can write F net x and F net y components, right? The mass is a scalar, so it's the same. Now acceleration is a vector, so it's going to be ax and ay. So these are the general form of Newton's second law in a component form. However, if we are smart and we choose the x-axis always parallel to the acceleration, or for that matter, the net force, then what we get is that ax is going to be actually the acceleration itself, and the y component will be 0. If we do that, then what we're going to have is our component form will be in a much more friendly way for us. F net x is going to be equal to mass times acceleration. What number am I? 4. And F net y is equal to 0. All right, 5. And this is the most used form of Newton's second law in grade 12 or first year university. All right. However, if this is only if forces acting on an object are in 2 dimensions. Okay, so which means you have in more than one direction. If you have only one dimension, forces acting just up or down or left and right, you don't really need components. Okay. And lastly, before we do some examples, let's talk about Newton's third law. All right. Newton's third law, I'm sure that we've dealt with it since grade 3, probably. Pretty much is that action, reaction, force, right? So it's written here: whenever an object exerts a force on a second object, the second one will exert an equal force in opposite direction of the first. All right. Very important, this one. This is something that we have problem with. The forces, the action, the reaction are acting on different objects, right? So if I were to draw a diagram showing Newton's third law, pretty much if I have an object A and an object B, on purpose I drew them different sizes, so it doesn't even matter which one is bigger, which one is smaller. If object B is, let's say, pushing object A with some force Fb, then according to Newton's third law, A will push object B with a force that is equal in magnitude and opposite direction. So that's a diagram, and if I were to write the equation representing Newton's third law, what we're going to write is that Fb is equal to negative Fa. All right, this is the mathematical relationship for Newton's third law. And how is that going to help us in problems? Well, it helps us eliminate some unknowns, right? Or find a common variable, especially between linked objects. However, here is an example that clarifies that action-reaction pair, right? So it says an ornament hanging on a string. So let's say we have a ceiling here, we have a string, and then we have an ornament hanging on it, right? And if we were to draw a free body diagram, and let's say that this is at rest, which means all the forces are balanced, okay? So if I were to draw a free body diagram for the ornament, I would have Fg pointing downward and Ft pointing upward, and they are in opposite direction and equal in magnitude. So my typical question that I would ask is, so here's a question: what is the reaction to Fg? And if you were to answer, and if I let you to answer, probably you would say that Ft is the reaction, right? Because it satisfies the fact that it is equal in magnitude and it's also opposite direction. However, Ft is acting on the same object, on the ornament, all right? So which means that according to Newton's third law, the force, the reaction force, should act on the object is causing the action, right? So let me explain that. So in order to answer, we have to answer a following question: what object causes Fg? What object is causing this force of gravity? And the answer for that is Earth. All right, the planet underneath. That's what is pulling. So Earth is causing this force. All right. So which means that the reaction should be on Earth. All right. So now the definite final answer is Fg prime, the reaction, is acting on Earth. So if I were to draw it, here is our ornament and it's being pulled, and here's Earth, right? So the Earth is pulling the ornament with a force Fg. Remember, this is object A, this is object B. What should the ornament do? Should pull the Earth up with some force F prime G. Okay. The same idea for the tension. What is a reaction to tension then? Well, what is causing the tension? The tension is being caused by the string, right? By the rope. So which means that the reaction should happen on the rope. Okay. So this is how you're going to tackle this type of questions to figure out the action-reaction pair. You always will look for the reaction on another object, the one that is causing the action. Again, practice will make you better at tackling this misconception.